Okay, guys, let's try to do this one. Um, it says a frictionless piston cylinder device contains 2 kilograms. Perfect. So now we can assume this first thing. So 2 kilograms there of nitrogen. Okay, so nitrogen is keyword for ideal gas. So in our course, we understand that nitrogen functions as an ideal gas unless certain conditions are kind of different, okay? And they are also telling me that inside this piston cylinder device, the pressure is 100 kilopascals. Meanwhile, the temperature is 300 Kelvin. So far, this is just raw data out of the sentence. Nitrogen is now compressed slowly according to the relation PV to 1.4. So this thing is now, it's compressed. I will try to depict what is happening over here. This is state one, and then something happens. Well, what happens is a very slow compression, okay, that goes from 1 to 2. So I will try to imagine this piston there, and if I'm not mistaken, a compression should be a reduction in the volume. So this is N2, this is N2, so something happened over there. Okay, let's just try to find, but whatever happened, it follows this rule. Okay, so it says 1.4 equals to a constant. I can also put P specific volume to the 1.4 equals to a constant because the rule doesn't change whether you are using volume in cubic meters or volume in cubic meters per kilogram. Okay, so the constant may be a different one, but the rule is the same one. So I can actually write that. Good. Now, until it reaches a final temperature of 360 Kelvin. So what I'm gonna put over here is that, well, let me just put some here. Now, T2 is 360 Kelvin. So it has gone from 300 to 360 Kelvin. Calculate the work input during this process. And they are telling you, okay, so let's just get the work when you go from 1 to 2. And I'm already gonna put this expression over here, or maybe let me just put in caps, so this thing is in kilojoules, or I can also put this using the specific work. It doesn't really matter which you're using. The information is the same one, except one is on a mass basis and the other one is not. So my preference is to use the specific because it's much easier, but it also depends on what is the data that they are giving you. So I will try to use the specific one, but I'm not sure if this thing's gonna work or not. So what I will try to put to solve this stuff is this. The work 1 to 2 is minus the integral PVV when you go from 1 to 2. Okay, so this type of work is called expansion, compression work. It's also called boundary work. Okay, so it is a work related with the change in volume. It's basically that. They don't say anything about an electrical battery. They don't say anything about a shaft. They don't say anything about a spring. So we can assume that this is the only type of work that appears in the problem. Okay, so with that, we need to just solve this integral. Oh, there's gonna be a problem out of that integral, but I can start using it. If I have this rule over here, I will try to put this. So P, I'm gonna put it explicit form. So V1 to the 4, okay? So I'm doing that. With that, I will try to put this thing, everything that I know about P, goes in there. So my expression for the specific work has to be this minus the C comes out of the integral. I'm doing this in just one step. And when you go from 1 to 2, what you will get inside is this. So you will get dV divided by B 1.4, which is also, just let me rearrange it a little bit. So this is also the integral from 1 to 2, and then V 1.4, and then dV. Okay, so this is what I get. The problem with this is first that I need to integrate, okay, but then I will need to get that C. That C is not that complicated. It comes from here. So the constant means that this is what it actually means. P1 V1 to the 1.4 equals P2 V2 1.4 as an exponent. Okay, so with that, you have a certain rule. Okay, so what I'm doing here, this is, let me introduce you to C, and this is C also, whichever, you can use whichever. So you will look back to this place and I see a lot of data here at once. So I think I'm gonna get C, this constant, out of state one rather than state two, because it seems that I don't have too much data there. Okay, so let me just try to arrange this. So now, because of this, the work, when you go from 1 to 2, the specific work is going to be minus P1 V1 1.4, and then the integral of V1.4 dV. Okay, so now there's just a problem of how to integrate this stuff. Before I'm going to do that, I will try to use I'm going to use the ideal gas in 1 and in 2 in order to solve this thing. So I'm going to start with this. Let me just move myself over here. Yep, a little bit, just a little bit. And then I will use another color. So from here, 1, you will get that P1V1 equals to RT1. Okay, this is what you will get there. Okay, let's just see what I have. I have P, I have T, and I have R. R is just data. So when they are giving you this substance, you can go to tables and find that they are, for that nitrogen is 0.2968 kilojoules kilogram Kelvin. So this is actually just data for the problem. So you know it. Now I'm going to get V1. So V1 is going to be equal to RT1 divided by P1. And if I put everything in there, hopefully is what I have. And if it's not, you can tell me out in the comments. So I will put the 300 divided by the 100. Therefore, V1, I'm going to put it here, V1 equals to 0.8904 cubic meters per kilogram. Good. I haven't solved anything with that, but at least I have more information. Okay, now what I will try to do is just to use something out of that, out of 2. So I'm going to use a 2, and for 2, oh, let me just do it over here. Okay, so I don't want to do it here. I'm going to do it over here. So 2. For 2, I will have P2V2 equals to RT2. If I had that, you will notice that the only thing that I have at the end is T2, which I already put, this 360 Kelvin. It's just this data. And that's the only thing that I have. So, yep, I have this fella. I don't have this one. I don't have this one. And I have that one. So maybe you will see this. P1V1 to the 1.4 equals to P2V2 to the 1.4. Okay? So I don't have this one. I have this one. I have this one. And I don't have this one. So it seems pretty complicated with that, right? So I will try to leave it like that and see if I can solve the problem without getting all this stuff. Okay, I will see if I can actually do that. If I cannot do that, I can just go back a little bit. Okay, so from here, I'm gonna go back to this place. I need to do this integral, and I'm gonna do it. But I'm gonna do it with the same color, which was blue. So from here, you will get 1, 2 equals to minus P1 B1 to the 1.4, which I already know them, okay? And now the integration will be V2 minus 1.4 plus 1, that's the way you integrate, minus V1 1.4 plus 1. I know that this thing is 0.4, but let me just put it explicitly like that. And here I will get the 1.4 plus 1, and that's the way you integrate this. So with that, you will see that this thing is actually a little bit, it's kind of, you know, we don't know this guy. We have this fella, and the only thing missing there is again this. And you will say, well, I'm gonna go back here, but it seems like you're stuck. Okay, I don't know if you see that, but it seems like you're stuck. So let me just do this. Hopefully you will like it. Maybe. I don't know. Maybe you will like it or maybe you don't. Uh, Instead of putting this equation, I want to put another equation. Let's just see this. V equals to RT divided by P. It doesn't really matter if it's state 1 or 2. It's always the case if you have an ideal gas. Okay. Now with that, instead of using P1, PV 1.4 equals to a constant, I will put this thing right there. And then I will use the states. What I mean by states that I'm going to use, well, let me just put it. So I'm going to keep working over here. So this is P RT divided by P to the 1.4. So that is a specific volume equals to a constant. But equals to a constant means that the thing at 1 should be equals at the thing at 2. So right now, I'm going to put what I mean by that. P1, 1, 1, P2, and RT2 divided by P2 to the 1.4. Okay? So maybe you detect it's the same thing that I have written is this stuff, but instead of seeing the specific volume, I'm just seeing another stuff. Hopefully you see that the R just goes out because it's the same one. And now I can do some algebraic rearrangement and it will look like this. Hopefully you can uh, take a look at this one. I will see this. So P1 is this 1 minus 1.4. Okay, so you see that 1 minus 1.4. T1 1.4 equals to P2 1 minus 1.4 and then T2 1.4. So now let's just see what we have. Yes, yes, nope, but yes. So instead of looking at here, because I don't have these two guys, but I have one of these guys, which is the temperature. So I'm putting this expression of PV to the 1.4. Instead of that, I will put it in terms of temperature. And now it allows me to get the pressure at 2. So I don't want to mingle too much on this, but you will see that this thing is, so P2 equals to P1, and therefore you will put T1 divided by T2. And this thing, in order to get rid of this stuff, maybe you will see that this thing should be this is wrong. I was just going to put it because what I'm going from here, this is 0.4, this is 0.4, remember, okay? And now this thing is not 0.4, this is actually 1.4. So if you wanna get rid of this minus 1.4, I need to use this. So P2 equals to P1, and this therefore is gonna be T1 divided by T2, 1.4 divided by minus 0.4. It's not the best, the more elegant way to put it, but it's actually what you will have over there. With that, you will see that P2, you can put all the information in there. You have everything that is needed over there, and you will see that this is 189.3 kilopascals. And if it's not, you can tell me. So now with that, I have the pressure at 2. And almost automatically, it's not that it's automatically, but with P2 V2 equals to RT2, you can get this fella that is waiting for you to be got. So V2 equals to RT2 divided by P2, and if you substitute all the numbers there, it should give you this 0.5644 cubic meters kilogram. Okay, so a lot of going around with this stuff. Okay, but now with that, you can go back to this place and substitute it over there. Now, I would just make some room for myself in order to put down here, I'm gonna put W1 to 2 equals to, let's just put values. allow me to put some values over there. So I'm gonna put what I know. So it's 100 times V1, and V1, I think you remember that it was the 0.89, 0.8904, okay, and to the 1.4, got it. And with this, let me just fill this with numbers, 0.5644, and its exponent is minus zero point 0.4, minus 0.8904, minus zero point 0.4 as an exponent, and this guy is minus zero point 0.4. Okay, so a lot of things to put in the calculator, and once you have that, this is what I got, and you will see you need to find if this thing is correct or not. I have a 44.52 kilojoules per kilogram. Remember, I was working with specific volumes, therefore I have a specific work out of this. Okay, so this is a positive work. It's a good thing that it's a positive because it means that work went in to the cylinder piston, and that means that because that's why the volume was reduced because somebody pushed it down. Okay, so this sign over here has some logic out of this happening over there. Okay, so with that, I already found what they were asking me. They were already asking me about this one. Let me just show you a shortcut. Maybe you're gonna grab your hair and want to take out your hair out of this, but there was a better, easiest way. The way to get it, I'm gonna write it here in red. Okay, so there's another way to do it. This other way, in this case, it was easier that way. It's not meant that every way should be done in this way. Okay, so I have delta U equals to Q plus W. That's completely correct. Okay. So if you remember your theoretical background, when you have PV to the K equals to a constant, therefore it means that Q equals to 0. At any moment, they are telling me that. They are not telling me that at any moment. Okay. Nonetheless, I can assume that just because of the number that this K has, or that this number has. This K for the nitrogen equals to 1.4. Therefore, I can assume that the process was done adiabatically. I can show you that it is adiabatic. So I will show you in this way. I will assume. So I'm going to assume that this thing is 0, and the problem will tell me if I'm right or wrong. I already have this file over there. I already know how this much. Now, the only thing that I need to get is this guy over here. And for an ideal gas, delta U equals to CV T2 minus T1. If you remember, I have T1 and I have T2, and CV is a little bit missing, but you can get it because CV for the nitrogen, you can get it in tables as 0.743 kilojoules kilogram Kelvin. Now, with these two informations, you can get that delta U when you go from 1 to 2 equals to 0.743 times 360, okay, minus 300. Everything is put in Kelvin. And with this, you will get that this value is actually, I have 44.58 kilojoules per kilogram. Now, this is pretty close to this value over here. Something can be changing because, you have a lot of things going on here. Okay, with these operations and to the 1.4 and with all these decimals over there. So some things can change. But the thing is that this was a shortcut. If you knew from the beginning this guy, therefore, assuming that the process was adiabatic, you would have just said delta U equals W1, 2. So you would have gotten this guy over here without using the integral, all this mammoth of a formula that you use over there. Just getting delta U will have gotten you the work. But it doesn't happen all the time. It was just at this case. Okay. So with that, we close this with this example, and we will see each other later. See you guys.